sheaves 01, BornCoarse, and it turns out that this category is a full localizing subcategory of all sheaves on BornCoarse. So we have the following pair of functors. So the homotopy functor H and from all presheaves to these coarsely invariant sheaves, and for the other direction we have an inclusion iota, and this is a pair of adjoint functors, and this result is it's okay.
Yep. Yeah.
Okay. And this pair comes from the Lurie's from the results from the book Lurie's book higher top theory. So this result is about presentable infinity category and small and localizing subsets or and local objects, and this is a some sort of reflective subcategory or some intuition from looks like this. Okay, and yeah. And now we are ready to talk about flasque spaces. Oops. This is a paragraph. The section, the next section of flasque. Sorry. Flasque. Spaces, and we need the following definition. So the definition of flasque spaces, we say that X in BornCoarse is flasque of flasque if it admits an endomorphism F from X to itself with the projections. Sorry, with the following properties. So the first property is that F and the identity morphism on X are close to each other. The next property is that for any U entourage from C, the following union over natural K. So here we assume that the set of natural numbers has 0. In some sort of French tradition, I suppose. Fk times Fk. Fk means that we apply Fk times. So Fk times Fk of U, and it should belong to C, the set of entourages. And the last condition that for any bounded set, there exists such K natural numbers such that the intersection between B and iterated F applied to X is empty. And in this case, we will say that the flasqueness of X is implemented by F. Flasqueness of X is implemented by F. Okay, now, of course, we should consider an example. So consider the set of positive numbers standard with a standard bornological coarse structure. Standard bornological coarse space. So it is a metric space, so we know that there is a standard bornological coarse structure. And suppose that X is some bornological coarse space. Then one can form the tensor product between these spaces. And it turns out that it will be a flasque. Okay, so we prove this fact. So we consider as F the mapping Tx to T plus 1x. So we just move the space. We want to move the space 0 infinity x to the right. And in this case, we have verified the third condition. So for any bounded subset, we can move this tensor product so far, and thus so we will have the following empty intersection. Okay, the second condition. For the second condition, so it is about so we should have entourage, and it is so just by the fact that our metric is translation invariant. So it is so the standard metric on this set is translation invariant. Yeah, but another example is that the space this is a usual Cartesian product. This is not flasque space. Flasque spaces. The flasque space is not flasque, since the third condition is not that doesn't hold. So fk of x intersected with b is not empty. For any k. So we can take for B the sets like this, where Bx is a bounded subset of X. And so it will be a fail. Okay, and of course we can consider a discrete subset. So we take n with the usual metric d, and one can form this space and d with the natural bornological coarse structure, which comes from the embedding into 0 infinity, and it follows that this space is also flasque for any x in BornCoarse. And the map is the same, of course. Okay. Now introduce the following definition: the definition of vanishing sheaves. So let E be a sheaf, which is a invariant sheaf. BornCoarse. And we say that E vanishes on a flasque bornological coarse space X if this value is a final object in the category of spaces. For any flasque bornological coarse space X. For any X in this category. And the following lemma is that has the same design as the previous one. So it tells us that the category of all such sheaves is a full localizing subcategory of invariant sheaves. So lemma. The coarsely invariant sheaves which vanish on flasque spaces form a full localizing subcategory of sheaves in invariant, coarsely invariant sheaves. So so we just apply the same proof as in the previous lemma. So we we take the result from Lurie's book and just add some extra morphisms for our set local morphisms. We know that E vanishes on X it's flasque X if and only if E is local with respect to the morphism appearing after application of Yoneda functor. So this is the map from Yoneda of empty set to Yoneda of X. And since Yoneda of empty set is isomorphic with the initial object, initial sheaf, it follows that so we should add such morphisms to the previous family, to our family of local morphisms. Family of morphisms. That's it. And thus we have the following pair of adjoint functors. So functor FL from coarsely invariant sheaves to the category of coarsely invariant sheaves which vanish on flasque spaces. So we will denote it by this. And the right functor is just inclusion functor. Consider an example. So suppose that X is a flasque. It follows that this map from the empty set to X induces an equivalence. Flasque of Yoneda of empty set to flasque of Yoneda of X. This is an equivalence. This is an equivalence. Yeah, this is by the fact that the morphism from Yoneda empty to Yoneda X is local, and hence this induced map is an equivalence. Okay. Now consider the fruitful, more general definition of flasqueness. More general definition of flasqueness. So suppose that X is bornological for space. X is flasque. In generalized sense, if there exists a family consisting of Fk parameterized by natural numbers including 0, fk from x to x such that f0 is the identity map on x. The next condition is that the union over all k, natural k, fk times fk plus 1 of the diagonal of x is an entourage of C. And the third condition that for any u in C, for any entourage u, the union is an entourage. And the last condition that for any bounded B, there exists k0 natural number such that for any k, k is greater than k0 or equal, this intersection with B is empty. So it's easy to see that this definition is indeed a generalization of the usual definition of flasqueness. So if you take as a family fk just f, then you'll get the previous definition. Okay, and now the lemma. So we can easily verify that the space, some space X is Flasquian in the generalized sense, but it turns out that it's difficult to verify it's in the setting of usual Flasqueness. So the following assertions are equivalent. X is flasque in the generalized sense. There exists f from and z tensor x to x, such that the composite f and iota is the identity map on x. So iota means that you take the inclusion corresponding to the inclusion of to pick a number 0. So you can embed 0 in NZ, and it will correspond to the morphism X to NZ tensor X. So determined by 0. Now the proof. So we prove that from the first condition, from the first condition the second follows. Let X be our space, flasque space in the generalized sense, and we have a family Fk. So in this case, we can define the map F capital in the following way. Fkx is just Fk of x. So F is a morphism. So we should verify that F is proper. For this, take a bounded subset B, K0 from N, coming from the definition of the generalized flasqueness. Then the inverse image of F of B under F is in the union this union. It's obvious, and it's obvious that this is bounded in NZ tensor X. So we have verified the properness. The next condition is that F is controlled. So C, the set of entourages on NZ tensor X looks like this. So it is generated by V, such that they have following form. They consist of pairs n plus 1, n in n, and cross the diagonal of x, and generated by diagonal on n cross any u in cross any entourage u. So yeah, and F of V is the following union. Which is an Cx by definition. By definition of our system being the generalized flasque system, and F of the other set. So we should prove that F of V is in Cx. V is here, and V of the other set, generating set, is in Cx also, and it is so. It equals just Fk times Fk of U, and of course it is in Cx. And for F0 of 0 is equal to identity, and hence F composed with iota is the identity map. So, and the other direction can be proved in the following way. in the same way. So if you have a map F such that the composite F and iota is the identity morphism, then you can define fk of x, of course, as fkx. It's easy. And now prove that the property of being flasque in generalized sense is coarsely invariant. So the same statement for the notion of being just flasque in usual sense is more difficult to prove, and yeah. Position the property of being flasque in the generalized sense is coarsely invariant. Proof. Suppose that X, as usual, is a flasque in the generalized sense, is flasque in the generalized sense. Then we are given family Fk, and suppose that G is a coarse equivalence, and H is an inverse map up to closeness. Then define the following family F prime K from Y to Y by the relation that F0 is identity F prime K plus 1 is the following composition G, Fk, and H. So it is the desired family. So one can verify all conditions. And now, if E is coarsely invariant sheaf which vanishes on flasque spaces, then it follows that it's the value of this functor. So lemma for any E coarsely invariant and flasque, and for any X flasque in the generalized sense, we get that E of X is isomorphic to the terminal object in the category of spaces, and this is proved by the previous property, by the previous characterization of being flasque in the generalized sense. by this line. So we can factorize the identity map from X to X. So X we can apply the map for iota, and so we can embed it into NZ tensor X, and after that we can apply F, and hence we get the desired factorization, and by the after the application of E, so we can apply E, and we get this sequence. And the fact that NZ tensor X is flasque in the usual way, in the usual setting. So we get that this is the terminal object. And now we have a factorization through the terminal object, and it means that, so, and the composite is the identity on E of X, and it means that E of X is isomorphic with the terminal object. Okay. Now to define the desired category of Motivic Coarse spaces, we should define the notion of U continuity. So the next paragraph, sorry, the next section. This is the section. This is section number 5. U continuity. And Motivic Coarse spaces. So we know that we can glue X from the components XU, where XU by definition is a bornological coarse space consisting of X, and as entourage, as core structure, we have one generated by U, and we take our core structure B coming from X, and we want to consider such factors. We want to consider such factors. E, say, is an coarsely invariant sheaves flasque on BornCoarse, that they respect colimits. So E, so we wanna that E of X to the limit of E of XU over all U in C, so that this map should be an equivalence. And if it is the case, we will say that E is U continuous. So we have this map to be an equivalence for any XCB, for any bornological coarse spaces, for any XCB. And we this is a definition. In this case, we will say that E E is U continuous. Okay, this is a natural condition, so we want this natural condition, and the next lemma, the next just a standard lemma, the full subcategory of such functors, such means that they are U continuous, and this subcategory is localizing subcategory in the category of bornological of coarse invariant flasque sheaves. So the full subcategory let's denote it's by SPC fancy X of, so, and this subcategory will be called the category of Motivic Coarse spaces. The category of Motivic Coarse spaces. Yeah, this subcategory of the category of coarse invariant sheaf, flasque sheaves. Of U continuous sheaves is localized. So we just should add some new morphisms, and so add the small set of morphisms so this is an obvious set. We just require that this we just add this set morphisms for any X in our category, and yeah, to the list for which sheaves must be local. Okay, and now we have, as usual, the following adjunction. So from the left-hand side, we have the following functor, say U, but it's not the forgetful one. So this is a clash of notations, but anyway, we will use this functor U from sheaves, coarse invariant sheaves flasque. on BornCoarse spaces. And yeah, we have the following junction between functor U and the inclusion functor. And now we can define the following generalized UNEDA functor. So it will be a composition of 5 functors. So the first, so we start with the category of bornological coarse spaces, and we wanna have a pre-sheaf on this category. And to do this, we of course should apply the functor, the usual UNEDA functor. After that, we should sheafify our representable pre-sheaves, but it can be omitted since our topology is a subcanonical one. But anyway, I write down this function. Say L, and now we are in the category of sheaves, and after that we wanna be in the category of the category yeah, the category of coarsely invariant sheaves. So we apply the functor H. After that, we apply the functor FL, and finally, we apply the functor U. So we move from the category of coarsely invariant sheaves to the category of coarsely invariant flasque sheaves, and after that, we are in category of Motivic coarse spaces. Okay. So remark here. Yeah. Just I said before, this L can be omitted. Oops. This can be omitted. Okay, and now we have the following functor from the category of bornological coarse spaces. So if we have a space X, then we have a Motivic coarse space U of X. So it is in BornCoarse, and it is in SPC fancy X. And the corollary here the infinity category Motivic coarse spaces, this category is presentable. So I'll soon give some intuition about presentability. So it will be a strict definition from Charles Resk. And without cardinality stuff. It's presentable and fits into a localization. Yeah, we have this junction from the category of pre-sheaves to the category of spaces. And here the functor is just inclusion. The second condition is that if we have a complementary pair Z, Y, complementary pair on X, then the square which comes from the application of U functor, U ZY, and this is U of a big family. Y is a big family, and the Cartesian squares is now becomes co-Cartesian one. So we have this co-Cartesian square in the category of Motivic bornological coarse spaces. And the next property, corollary, if a map from X to X prime is an equivalence of bornological coarse spaces, of course, then the map uneda of X to uneda X prime is an equivalence in the category of Motivic bornological coarse spaces. And the last property, that if X is flasque bornological coarse space, then uneda of it is an initial object. In that category. Not the last statement, but it is so for any X in bornological coarse space. So uneda of X can be represented via co-limit limits of uneda of XU over all U and C. Yeah. Okay. And now and from this corollary, one can derive the corollary in the style of Lurie's book. So that we get an equivalence between functors which preserve small colimits functors from Motivic Coarse spaces to C, where C is an any infinity category. And the full subcategory of full subcategory of all functors that preserve small colimits from the category of pre-sheaves on BornCoarse to the category C. Okay. Now, so now I suppose that I can give some definition of presentable infinity category. So I recall this definition. So what is the intuition of being presentable? An infinity category is presentable if and only if it is equivalent to one of the form. So we have some generators and relations. C stands for generators and R for relations, where C is a small infinity category, R a set of maps in the category of pre-sheaves on C, valued in the category of group poets. And this guy P of CR is the full subcategory, of pre-sheaves on C, spanned by F. F is an pre-sheaf such that the induced map from the category of pre-sheaves from the homes, spaces, pre-sheaves from Y home space, the home space in the category of phrase shifts from Y to F to the category of to the appropriate home. And this is an isomorphism of infinity group words for any F and R. Is an isomorphism of infinity group words for any F in the set R. And so one can show that this inclusion admits left adjoint. So this category PCR is complete and co-complete. So the fact that it is generated by some elements of C and with relations in R, it means that we have the following map. So, oops. So consider the category of colimit preserving functors, small colimit. From this category PCR to some co-complete infinity category, say D. It is a co-complete infinity category, and we can map it into the category of functors between C and D that sends relations to isomorphisms. Fun tilde functors that send relations, that is elements of R to isomorphisms. Okay, and how does it work? It's easy. So if you have a functor F from the left hand side, then you get the functor from the right, just applying the left Can extension. So if you have F, say F here, then F, this F modified of F is an isomorphism for any F where F, this F is the left Can extension of F along iota, where iota is just an inclusion of C into the category of all phrase shifts on C. So we have the following diagram. C embeds into phrase shifts on C, and we have a functor F, and we have a left Can extension. F along iota. Yeah, this is the definition. Now we are going to talk about some properties, but probably I'll skip it. Yeah, I'll skip it. So now, so we will talk about Motivic Coarse spectrum. So our aim is the category SPX fancy X, the category of Motivic Coarse spectra, and to form it we need a stabilization. So we need an analog of the factor sigma. The factor sigma. So we will construct the factor Yoneda stabilized from the category of bornological coarse spaces to the category of spectra, coarse Motivic spectra. So, and to do this, I recall the standard scheme. So the first section here is the stabilization. So if we have a category of spaces, then we can construct the category of spectra, and yeah, it can be done by the localization, just by yeah, just firstly define the factor sigma. So this standard factor from the category of pointed spaces to the category of spectra, and to do this, consider just the co-limit diagram. So we have a map from the terminal objects to x, and it can be mapped to the map between these terminal objects and these points, and we just can form this co-limit of the diagram. So just form a push out, and we get the definition of sigma x. So this is definition is a standard one, as in the setting of model categories, or but in this case we consider the setting of infinity categories, but of course they are equivalent in some sense. Yeah, and after that we can define the following category of spectra just by the inversion of the factor sigma. So we just take our spaces and invert this functor, it means that we just stabilize it. So by definition, we take colimits of the following of the diagram of the form spaces. Oops, sorry. Spaces to spaces, etc. Yeah. So we have the following adjunction, the standard adjunction between the category of spaces and the category of spectra. From the left-hand side, we have the functor sigma infinity plus, and from the right, omega infinity, where sigma plus is the composition. So this is the composition. We start with the category of spaces, and after that we add the point. And after that we apply the stabilization, and we get the category of spectra. Okay, and this scheme can be applied to the case of Motivic bornological coarse spaces. So construct this category, and it will be, as in the standard case, large, presentable, stable infinity category. And so the functor sigma is the same, and we define the functor sigma mod Motivic at the composition from the category of Motivic coarse spaces. After that, we add points and apply this functor sigma. So okay, and also in this setting we have an adjunction between sigma and omega. So sigma from coarse spaces to the category of spectra. Yeah. Let's see. Okay. And we can define some sort of universal homology theory. So the functor the stabilized uneda functor. The definition. Uneda stabilized of x is just the composition of sigma Motivic plus and the usual uneda. No, not usual, but the uneda coming from the previous considerations. Okay. So yeah, this is it. Okay. Now so some results about complementary pair and fiber sequences can be obtained, and I think I can skip it. So let's talk about the notion of homotopy invariance. So we introduce the notion of coarse cylinder and we discuss this general this notion of homotopy in this context. So homotopy and variance. Okay. To define the coarse cylinder, the cylinder object in this category, we should take some functions. So we consider the standard bornological coarse space consisting of positive numbers, and consider some bornological maps P plus from the bornological coarse space X to this set, and P minus. So this is like top and bottom. Yeah, and one can consider the following tensor product between R and X, and we can subdivide it in some sense. Yeah, and I'll give the following definition of the coarse cylinder. So the coarse cylinder IPX is defined as a subset. So by definition, IP of X consists of such pairs TX from R tensor X, such that C is between P minus of X and P plus of X. So yeah, and this is a subset of tensor product between R and X, and it is equipped with the structure coming from R tensor X, and one can verify that the projection from the cylinder to X is a bornological coarse. Sorry, this is a of course morphism, and this morphism is indeed an equivalence. So lemma, this projection is a morphism. So this is a standard. This can be verified in some standard way, and so proposition tells us that a coarse cylinder and the projection induce an equivalence between stabilized UNEDs. So UNEDA stabilized of the coarse cylinder to the UNEDA stabilized of X is an equivalence. Is an equivalence in the category of spectra, and yeah, and but I think that the proof can be omitted. Yeah. So, and now if we have a cylinder IPX over X, cylinder over X, Then we can consider the following maps I plus minus from this cylinder to vice versa, from X to the cylinder. So we'll just map this X to P plus minus of X. And if it is the case that P plus and P minus are controlled, so if are controlled, then we have the following definition. So suppose that F plus and F minus are two morphisms from X to X prime, and so we say that they are homotopic to each other. They are homotopic to each other if there exists a pair of control and bornological morphisms P such that and of course homotopy H from the cylinder to X prime such that F plus minus can be obtained by the substitution of I into H. So this is an analog of the standard definition, or of usual homotopy. And and one can notice that the following composition between pi and I plus minus is the identity map on X. And from this quality, one can derive that it is easily follows that the functor the stabilized unit functor sends I plus minus to equivalent maps. Just by the reason that ID is an equivalence, and this relation. Okay, and suppose that F plus and F minus be two morphisms, and they are homotopic, so corollary. Suppose that F plus and F minus are two homotopic maps, then stabilized unidas are the same, are equivalent. So it follows from the from this observation. And the next standard definition, we say that F and G, X from X prime and G from X prime to X are just F is a homotopy equivalence. if there exists such G from x prime to x, that the composites are homotopic to their respective identities. So F as usual. G on x prime and yeah, and the stabilized unit of Hunter sends homotopy equivalences to equivalences. Sends equivalences to equivalences. Okay. Okay. Now consider an example. So suppose that m is a natural number and n is greater than 1. And consider the union, the disjoint union of balls of some radii. So R from I to the set of positive numbers. I is a some set, and consider X to be following disjoint union of balls centered in different points. As an I, and then we define a coarse structure on X to be generated by the family of entourages on entourage U tilde I of the form where I is an I and URI is an entourage UR. This is an entourage consisting of all points with the of all pairs such that the distance between them between each points in such in each pair is less than R, and yeah. Yeah, this is some entourage UR, but indexed by I, and so just we imagine some disjoint union of balls, and so and now we can consider the following discrete subset consisting of all centers of these balls, and it turns out that this discrete set is coarsely is equivalent to our space. So now consider the map iota from the index set I to the set X. So we just choose a center for each ball, and this iota is homotopy equivalence. So with the projection, so we have a projection pi from X to I. We we project whole ball to the center, and this is some sort of inverse map. Yeah, and the composite is the identity morphism on I. And now we should construct a homotopy between iota composed with pi and identity on X. And we will do it. So consider a point Ix. So this point X lives in the ice ball. So X in B, C, I, R of I. And consider the following functions. As Pi, we take 0 function, and for the function P plus of Ix, we just take the norm of X, the standard Euclidean norm. And we can form the coarse cylinder IPX. Cylinder I PX associated to the pair P minus P plus. And the desired homotopy H from the cylinder to X will look like the following. H of C and AIX will be I0 in the case when X equals 0 and IX minus C X divided by the norm of X, and X is not equal to 0. Yeah, and this is a morphism, and P plus and P minus are controlled, and so this is a homotopy from the composition and the identity map on X. So you take Z to be 0 or 1, and or not 1, but norm of X, and yeah, this is it. So we can, so thus the stabilized uneda of the set of all centers of these balls is equivalent. So uneda stabilized of it is equivalent to the uneda stabilized of whole X. So this is an analog of the statement that for example, a plane is equivalent to the integer points of this plane, or any n-dimensional space Euclidean. Okay. And now we are going to talk about axioms for coarse homology theory. So this is a section. This is section 3. Section 3. Axioms for coarse homology So for the cohomology theory, there is an article of others article and the date I suppose 2022 or so, some recent work about the cohomology case, and you can look it's from archive, for example. Okay, but now we discuss the case of coarse homology theory. So suppose that we have co-complete stable infinity category C, co-complete infinity category. And we have functor from the category of bornological coarse spaces C. So this is a function. And for a big family Y, one can form E of this big family just as a colimit. And we say that E of xy is the cofibration, cofiber of the map from E of y to E of x. And now the main definition of this section is that E is a coarse homology theory if it has the following properties. So the first one is that is about excision. For any complementary pair Z, Y, one has a morphism. One has a morphism, which is an equivalence. So this is an equivalence. The second condition is about coarse invariance. So if X to X prime is a morphism of bornological coarse spaces, then the induced map should be an equivalence in C. The third one, vanishing on flasqueness. So if X is a flasque space. Then E of x is isomorphic to 0. And the last condition is about U continuity. Sorry. So this is a natural axiom. You know that if you have a whole space X, then you can subdivide it or something like this, and you can glue it via the colimit construction from some XU, and so you have an equivalence. And we wanna have the following isomorphism after applying E of x should be isomorphic with the colimits of E of xu. Yeah. So, but the excision axiom can be reformulated via the push-out condition. So, the excision axiom can be replaced by the following condition. So consider the diagram of the form. And we require this diagram to be push-out square. Okay, so I think this is a logical point to stop.
Okay, thank you so much for this wonderful talk. Stop the recording.